All right, so right now, wow, my voice cracked. We are starting the chapter 13 handout, and chapter 13 is all about conjugation. So first and foremost, what is conjugation? That essentially just means we have multiple double bonds in a row that can share electrons amongst each other. So I have an extra page so I can show you what I mean. If it would write, that would be so awesome. Okay. So in chemistry, we have this lovely thing called resonance, right? And when we have a double bond, the resonance can either go to this side or to this side, right? And remind me, what hybridization is required to do resonance? What do we think? Either sp2 or sp. Awesome. So we cannot do resonance with an sp3 carbon. So if we have, ignore my dog. If we have this double bond, we can only go here or here because this is sp3, this is sp3. However, oopsie. If we have two double bonds with a single bond in between, you can move these electrons here, and you can move these electrons here, because all of these are sp2. So this is what we call conjugation. And I'll write a little note. It's when we have two double bonds with one single bond in between. So any questions about just what is conjugation? Also, can you guys hear like the weird crunching sound in the background? Because Bear is playing with a toy and it's extremely loud to me, but I don't know if you guys can hear it or not. Not really? Okay, cool. If it's not like super annoying, then I won't take the time to go deal with it, but okay. So, if we're good with conjugation, we have two more things we have to talk about. So, we have the same molecule, and now we have two double bonds that are more than one single bond apart. So the difference here is we have an sp3 carbon in between the two double bonds. So this has its own name. This is isolated. So when we have two double bonds, and I like to say this in two different ways because sometimes people like one explanation and not the other. So it's either two double bonds with more than one single bond between them, aka with one or more sp3 carbon between them. So does everyone kind of see the difference between conjugated versus isolated? Yes? Okay, cool. So the last thing we have to deal with is essentially like the opposite of isolated. So we have one carbon that has multiple double bonds attached to it. So we're going to call this one cumulated. And someone said, what's the one in the middle referred to as? So if you're talking about this one, this is just one single double bond. So it's nothing special. It doesn't have a special name. I just wanted to show you like what the difference is between one double bond and two double bonds in different orientations, if that makes sense. Okay, cool. So cumulated double bonds are when we have two double bonds on the same carbon. And so I'll zoom out just a tad so you can see them all together. And so do we kind of understand the difference between these three things?
Yep, I understand.
Okay, cool. So I'm just checking the chat to see if there's any questions. So what's the main difference between conjugated and isolated? So conjugated means that the two double bonds have one single bond in between them. And isolated means there's more than one single bond. And so basically here you can do resonance, here you cannot do resonance because this sp3 carbon blocks the resonance. You can think of it like that. And no, cumulated is not conjugated because for conjugated you have to have one single bond. For cumulated, they're attached to the same carbon, so it's not the same. But that's a good question. Cool. So we're going to make a little note box here. And we're going to talk about the stability. So based on what I told you guys about resonance and all this stuff, which one of these three do you think will be the most stable?
Conjugated.
Yep. And then just by looking at these three, which one do you think will be the least stable?
Cumulated.
Yeah, cumulated, or the last one. Because it's just kind of ugly, right? And we don't want ugly molecules. If you want a scientific reason for that, basically, here we have resonance, so resonance is the best. Isolated is whatever, there's nothing special about it, they're just kind of far apart. And then cumulated, there's so much happening. There's so much attached to one single carbon that it's like, it's not stable. There's so much going on. We're not happy. So the order of stability goes conjugated, super stable, isolated, meh, cumulated, not stable. Sorry, that was getting on my nerves. Any questions about the order of stability? It doesn't seem like there is, but I will give you like a couple more seconds while I sip my tea. Cool. So I'm going to scroll back up to the handout, and we're going to go over these questions. So I am going to like circle one of these, and you guys are all going to tell me what it is. And you guys are already ahead of me, so you are correct. This is cumulated. What do we think about this second one? Isolated. And what do we think about this last one? Conjugated. I agree. Alrighty, so a little bit harder this time. What do we think about this one? Isolated, I agree. Okay, what do we think about this one? Accumulated. Awesome. And what do we think about this last one right here? Conjugated. Perfect. You guys are already masters at conjugation. Give yourself a round of applause. Woo! Okay. So now we're going to rank them in order of stability. And since we kind of already talked about like conjugated, isolated, accumulated, I want you guys to tell me most to least stable, what would the numbers be? And I want you to say it in the chat. I'll give you like 1 second while I close my door so Bear can't be here anymore. So awesome. You guys are right. The order would be 1, 2, 3. And it has occurred to me a couple days ago that this was already in order for you. So all I'm going to do is this. So number 1 is the most stable because it's conjugated. Then we have isolated. And last garbage yucky one is accumulated. So guys, we're all on point. Perfect. Good job. And so for this second one, it's a little bit more challenging. So I'm going to help you kind of walk through it, right? So we said that conjugated is the most stable, right? But now all of these guys are conjugated. So we have like a second level, right? We can't just say, oh, conjugated is the most stable. So when we're looking at the difference between these, what do you think we're looking for? That was a little bit vague. I guess when we're trying to figure out which one's most stable, what are we looking for? So someone is saying confirmation, someone is saying configuration, because that's what it says right here. I like your thinking. Okay, and some people are saying which one has the most resonance. Exactly. And so just by looking at this and not actually doing resonance, how do we know which one has more resonance? Excuse me.
Is it the branching we have to look at?
So branching, that's a good thought, but it's even simpler than that. Some people are saying the rings. No, not necessarily. I mean, yes, but even before we go into like rings versus linear, whatever, what's the biggest difference between like this one and this one? The number of double bonds, exactly. So the more double bonds we have, I'll write that in the corner. More double bonds equals more conjugation. And another way that he says that is the level of conjugation is higher. So the more double bonds, the higher the level of conjugation. So the higher the level of conjugation, the more stable. So basically, the more double bonds we have, the more stable this is going to be. So with that in mind, I will give you a couple seconds. Please give me a guess of most to least stable. Yes, awesome. A couple people said it. I'll give you like 1 more second if you're still thinking about it while I sip my tea. And then we can go over it. Perfect. So I'm going to zoom in just a tad. So we can see that here we have 3 double bonds, here we have 2, here we have 4, and here we have 5. So you guys said, because of the number of double bonds, the most stable is number 5. Is number 4 because it has 5 double bonds. And then we have number 3. And then we have number 1. And then we have number 2. And I absolutely agree with your order. And now some people were onto something when they mentioned the rings. And we're going to cover this more next chapter in chapter 14, but I do want to give you guys this little tidbit so you can think about it until then. So, these 2 rings are actually aromatic. And you guys aren't expected to know that right now because we haven't gone over like what aromatic is, how to tell whether something's aromatic, but I'm telling you they're aromatic. And all you need to know is that conjugation is super, super stable, but aromatic is even more stable than conjugation. So let's say we had a regular old benzene ring, because you should be familiar with that one. And then we had this, right? So both of them have 3 double bonds in conjugation, but this one would be more stable because it has this added aromaticity. So again, if that's kind of confusing because you don't know exactly what an aromatic ring is, that's okay. We're going to talk about it next chapter, but I believe this is something he talks about in class, so I wanted you guys to have that little bit of knowledge. How are we feeling so far? Good, bad, okay? Someone said good to know, smiley face. You guys are so sweet. I love the interaction. Okay. Gonna take a pic? Yeah. I figured this is a good place to stop and take a picture, so I'm gonna zoom out just a tad so this page number thing is not in the way. So if you want to take a picture, please feel free. Alright, so now we're going to talk about configuration and conformation. And so this is a pretty straightforward chapter in my opinion, until we get to the very end, but that's don't think. So conjugation is pretty straightforward, but this stuff gets really confusing to students at first, especially if you have trouble seeing things in 3D. So if you have any questions about configuration and conformation, no matter how silly you might think it is, please ask so you don't get super confused. But I will try my best to keep everything super straightforward. Alright, that being said, in Orgo 1, you guys were introduced to this, but you were not introduced to this. So when we talk about a double bond, we can classify it as cis or trans or E and Z, right? So you might not remember this, and that's okay if you don't, but do you remember if that was configuration or if that was conformation? So when you were defining a double bond, was that configuration or was that conformation?
I think it was confirmation.
Okay. A couple people said that in the chat too. So maybe they might have used these 2 words interchangeably. I honestly don't remember Orgo 1 that well. It's been a long time. But we're actually going to call this one configuration. And I'm going to do configuration in blue. And the reason I think of this as configuration is because configuration is kind of more like stable. You know what I mean? Like, you can't really change back and forth too much. Like, something's configuration is solid, written in stone kind of thing, right? And we know that this is true for double bonds because we cannot rotate across the double bond. So we cannot flip-flop between these two. So that's why I kind of think configuration, that's more stable, it doesn't change. So that's when we have the double bond in the middle. So configuration, double bond in the middle. I didn't give myself enough room, but again, what else is new? The other way I say this, that's kind of silly, but here we basically have a single bond sandwich with a double bond in the middle. So you can think of configuration as a single bond sandwich. And I'm just going to move this over like a tad so I can draw on the double bonds. So when we're doing configuration, it's a single bond sandwich with a double bond in the middle. That's the important part, right? The middle is the important part. So whenever we do configuration, I'm going to go ahead and highlight the double bond because that is what we care about. And when we're talking about confirmation, when we're talking about configuration, and we're talking about the double bond, how do we decide whether we name it E or Z or cis or trans? Like, what do we have to do to define it? And then while you guys are thinking that, someone made a really good point in the chat, and they said the way they remember it is conformation has an M, and that means multiple bonds. So we can definitely say that conformation means multiple double bonds. Thank you for that tip. That's really helpful. Okay. And now back to how we name it. So you guys got it right on the head. You hit the nail on the head. So if we have the substituent on the same side or the opposite side, that's how we figure out the name. And I'm going to say like one step further, and I'm going to say the most important substituent. And what I mean by that is here we have a hydrogen and a hydrogen, right? And the priority group is the one that has like the highest mass, right? And so the methyl and the methyl are considered priority. And if the priority groups are pointing opposite one another, we can call that, what do you think? Trans
E.
or E. Awesome. And someone made a really good point, and I ignored it for a second, but I'm going to give you the credit you deserve. So, for this one, they are pointing on the same side, and as someone in the chat said, is Z stands for Z same side. So, that's how I like to think about it. The other way we can call it is this. And that's when the priority group is on the same side. And something I want to mention is in Orgo 1, I don't remember if they were super strict about when to use cis versus E, Z. But in this class, we're basically just going to say, like, if it's configuration, we're going to use EZ just to kind of keep things simple. Cis and trans is, like, a little bit more specific, like you can only use it for specific cases. You don't have to worry too much about it. Like in this class, if you call it trans or cis, you're not going to like get it wrong, but just know that E corresponds to trans, Z corresponds to cis. And we are going to make a couple points about this. So point number 1 is we can not easily flip between configurations. So we cannot really go between E and Z. You would have to like do a big reaction to make that happen, right? And the other thing is, we're going to figure out which one is more stable. So between E and Z, which one do you think is the most stable?
Yeah, E because of sterics, right?
Yep. So trans, aka E, is more stable. If you would write, that would be awesome. Because of sterics. So if the big bulky groups are pointing opposite directions, it's much more favorable than if they're pointing in the same direction. So perfect. You guys did an awesome job for configuration. And so now we're going to talk about conformation. And as someone said, M in conformation stands for multiple double bonds. So that's how you can kind of remember it. And so whenever we talk about conformation, we are going to go ahead and talk about the single bond in the middle. So again, when we define something's conformation, we're going to talk about the single bond in the middle. Because we're always talking about the middle. And you can think of this one as a double bond sandwich with a single bond in the middle. And as we know, the middle is the most important part. That's why we focus on the single bond. Okay. So, when we're defining this guy, we cut down the middle just like we did for our double bond. And we are going to look at the relationship between the two double bonds. So the two double bonds are opposite one another. These two double bonds are on the same side. And so the naming of this is similar to configuration. We're going to call it S trans and S cis. And before you guys ask, so I don't know scientifically what the S actually stands for, but how I like to remember it is we're talking about the single bond in the middle. So S stands for single bond. So the single bond is trans versus the single bond is cis. Oh, it is single bond? Hell yeah, dude. Killing it. Big brain energy right here. Okay, I'm sorry. So, between S cis and S haha, I love to see when you guys do those little like emoji reaction things because I'm like, I'm funny, dude. Okay, sorry. So, between these two, which one do we think is going to be more stable? S trans, yes. So S trans is more stable, and shockingly, it's for the same exact reason. So, sterics, it's more stable when we have the two groups pointing opposite sides because they're big, bulky groups. All right. The other thing I want you to remember is that we have a single bond in the middle, and single bond has free rotation. So we can flip between conformations. So theoretically, I'm going to do this a different color just so everything's not like looking the same. Theoretically, we have free rotation across this double bond. So we could flip between S cis and S trans if we wanted to. And we are going to do that in later chapters, so keep that in mind. Store that in your big brain. Okay, I'm done talking for now. I will let you guys take a picture or write it down, ask any questions, and then we're going to do some examples. Okay, so someone asked, why is it called S-trans? And basically the S stands for single bond. And we're defining the I'm going to start over. The S stands for single bond because we're defining the single bond in between two double bonds. Okay, so someone said, how do you know whether something is E or Z? So we're going to do a couple examples so you can actually see like how to define it. If you're still confused after that example, let me know and I will cover it one more time. All right, so I'm going to go ahead and draw out the example. Please give me like, or I might have the example. I don't. Darn it. So let me just draw it real quick. Actually, I'll let you see this for one more second, and I'm just going to pull up the example because I don't want to draw it. If you guys couldn't tell, I'm feeling very lazy today. Oh my gosh, if it would not be annoying, that would be the coolest thing in the whole world. Alright. I'm gonna stop sharing for a second just in case it, like, does anything weird. Oh, I forgot to send you guys actually the attendance link, so I'm going to give you that while I insert this example. Pretty please, you know the drill. Do this. Someone said me too. I don't even remember what I said, but I'm glad it was relatable. Okay. And let me share my screen again. It's probably going to stop the recording when I start sharing, so I will keep an eye out for that. Haha, I win. It didn't even stop the recording. Cool. Alrighty, folks. So, it is 12:15, but I do want to give you guys a chance to look at this. So, I want you guys to take 2 minutes and look at these four. And based on what we just talked about, I want you to go through and define configuration and confirmation. Don't worry about like putting them in order. Just worry about like figuring out which one's E, which one's Z, which one's cis, which one's trans, things like that. So I will give you 2 minutes to look at it and then we will cover it together. So here, ta-da. I would put you in groups, but... And yes, so while you're at it, someone made a great point. You can also think about like which one's isolated, which one's cumulated, which one's conjugated. While you're doing that, I just thought of the dumbest thing. I was like, let's do... Never mind, I'm not even gonna... Just do your thing. Do 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 do. I'm really bad with silence, so I'm just gonna keep talking and hope that doesn't bother anyone. So I'm really gonna show you guys my age with this, but like, I'm sure most of you know what TikTok is, right? And because of TikTok, I have the freaking Backyardigans song in my head. And so, if anyone can relate, please let me know so I don't feel crazy. Everyone's like, okay, so I think that's enough time. I think that was 2 minutes. So, let's go through it, shall we? Bam, we're gonna zoom. Now it's in my head, haha. Okay, I'm sorry. Alright, so for this first one, first I want you guys to tell me, is it conjugated, cumulated, or isolated? Conjugated, I agree. Awesome. So now that we've got that out of the way, let's do the configuration. So let's highlight double bonds. And you guys tell me, this double bond on the left, is it E or is it D? D. Is it E or is it Z?
It's Z.
It is. Are you sure, Z? Z stands for the same side. Maybe I could have also misread.
Oh, never mind.
Okay. Yes. But good for you for actually giving an answer. Proud of you. So this one's actually going to be E because the single bonds are on the opposite sides. And this one is also going to be E for the same reason, because they're pointing opposite directions. And then I'm going to do the conformation in red, just so there's some contrast. So when we're looking at the conformation here, what is going to be the conformation? Conformation doesn't even feel like a real word anymore. I said it so many times. Are the double bonds... Oh my god. Sorry, I just had a stroke. Are the double bonds pointing...
Trends, right?
Yes, thank you. Thank you for rescuing me. So the double bonds are pointing opposite, so they are S trans. Ta-da. All right. So the next one, is it conjugated, cumulated, or isolated?
Isolated.
Okay. Isolated, I agree. So we can't really do any conformation, so we're just going to do the configuration. And I want you guys to tell me, what is the configuration here? And then someone had a question. I saw your question. We'll do it in like 1 more second. So what do you think about this one? Is it E or Z? Oh, it's neither. Yes, you guys got me. So we cannot give this one a configuration because there is no priority group. So we have 2 hydrogens here. We can't pick a priority group, so this one doesn't get E or Z. You guys caught me. That was a trick. That was kind of mean of me, but you guys are even ahead of me. All right. So what about this one? What do we think of this guy? So yes, I'm gonna say E. I agree. Because they are pointing opposite directions. And so going back to this one for a second, because someone had asked me, why do we have trans here? Like, why is this S trans? Because if you kind of orient it in your head, I know sometimes it's hard to see, but when we look at this single bond, and then we look at where the 2 double bonds are facing, they are facing opposite directions from one another. So that's why it's going to be trans, because they're facing opposite one another. And then we can kind of think about it the same way for the double bond. When the single bonds are pointing opposite directions, we know that it's E. And then, okay, so I think when you say draws the line, I think you mean like this, right, to define it. And I like to draw that all the time just to also keep it in check, but we were kind of running out of time, but I can definitely do it if that helps you see it. So when we have this line in the middle, we know that one is facing up, one is facing down, and so they're opposite, and that's why it's E. And so let's work on the third one, and I'll go ahead and draw the lines. So before I even try to trick you, can we do a configuration for this one? So someone said something, but it got really cut out. Everyone else said no, so I'm going to assume that was the general consensus. So no, we cannot, because again, we have two hydrogens. Awesome. So here, if we draw the line in the double bond, these two single bonds are pointing the same direction. So is it going to be E or is it going to be Z?
That one is Z.
That one is Z. I absolutely agree with you. So we're going to go ahead and say Z. So can we come up with a conformation here? And remember, conformation is when we focus on the single bond. No, a couple people said no, and I totally agree with you, because this is not conjugated. It's what? Isolated. Perfect. I 100% agree. It's isolated, so we cannot define anything for conformation. Cool. So, is this one conjugated? And, someone asked a question, but then everyone said no, so give me a second to scroll. All right, so the question is, so is it always just one single bond in between for conjugated? Yes. So it only has to be one single bond in between for it to be considered conjugated. And that's the same thing for conformation. So it has to be just one single bond in the middle. All right, so this one is isolated, no conformation. Cool. And can we do any configuration here? No. Awesome, because now I have like that trick on both sides. Neither of these have a priority group. These are both hydrogens. These are both hydrogens. So we can't define anything here. Last but certainly not least, we have this one. So is this one conjugated? Yay or nay?
Yeah.
Yep. And a couple people also said yes in the chat. I absolutely agree. So the reason is we have double bond, single bond, double bond. So we have a double bond sandwich with a single bond in between. So let's start out with configuration. So we have these two blue double bonds. The one on the left, we have two substituents that are facing the same direction. So is this E or is it Z? It is Z. I agree with you. Awesome. And then on this side, we have actually pointing opposite directions. So what do we think? Is this E or is it Z?
That one is E.
It's E. I totally agree. I agree. All right. So for this one, since it is conjugated, can we talk about conformation?
Yep, there's confirmation in the middle there.
Yep, and someone said in the chat that they think it's trans. let's draw the line just so we can double check. So yes, the two double bonds are opposite one another. They're pointing different directions. So I totally agree. We're going to call this S trans. So look at you guys. Look how much you did. That's awesome. All right, so now we're going to go in real quick and we're going to figure out what the order of stability is now that we got all of this figured out. But does anyone have any questions before we do that? So any questions on E, Z, cis, trans, what the heck we did? I know that typing it up sometimes takes time, so while you type it up, if you have a question, I have a question for you. So when we're talking about just a double bond stability, without cis, trans, anything like that, how do we figure out, like, you know what, that's a weird way to ask it. Is a double bond more stable if it has more substituents or less substituents? And then someone asked a question. I will answer it after I finish this thought. So yes, I agree with you guys. So for a double bond, more substituents equals more stable. So keep that in mind. And someone asked, so for conjugation, we have to find each side as E or Z. So yeah, basically for conjugation, we look at the double bond and we have to see if the single bond is pointing the same or opposite. If it's the same, it's Z. If it's opposite, it's E. Okay, so first thing is first. We know that conjugated is more stable than isolated. And so I'm going to go ahead and put a little star by the conjugated ones. So automatically, we know that 1 and 5 are going to be more stable than the rest of them. And between those two, we know that trans is more stable than cis. And so here we have E, E, trans. And here we have Z, E, trans. So between 1 and 5, which one do we think is going to be more stable?
1.
1. Awesome. So I'm going to say number 1 is the most stable. And just to reiterate, 1 is more stable than 5 because it is EE, while the other one is EZ. And we know that E is more stable. Okay, so 1 is the best. And then we have 5. Oh my goodness. If I could have any consistency, that'd be great. All right, so after 5, we have 2, 3, and 4, right? And we know that all 3 of those are isolated. And that's why we automatically knew they were less stable than 1 and 5. If we zoom in on those two, we have 1 double bond with only 1 substituent. We call that monosubstituted. So I'm going to say mono. And we have a disubstituted. Mono. Di. Mono. Mono. So between these, which one is the least stable? Yes, I agree. So this one is going to be the least stable because we know the less substituents, the less stable. This one has 2 monosubstituted, so that one is yucky. Ew. So let's go ahead and say for is last place. Okay, so now between 2 and 3, we have 1 monosubstituted, 1 disubstituted. We know that the monosubstituted can't have E or Z. So we're going to look at the configuration of this double bond. We have 1 E and 1 Z. So which one do we think is more stable between 2 and 3?
The E, then the Z, and then 4 is last.
Yep, and a couple people said that in the chat as well. I totally agree. So, number 2, number 3, and then we knew that number 4 was going to be last place because it's so yucky. In scientific terms, of course, it's yucky. So please take a moment, look at it, think about what we talked about, and if you have any questions, comments, or concerns, let me know. And I will give you that second to think about it, but so now it's 12:30. So we're going to move into the other session, which is kind of annoying, but I did want to keep track of the recordings and everything. So if you don't have any questions, I'm going to move into the 12:30 extra SI session slot, and I will see you guys and gals and everyone else there. Cool? Okay, cool. Adios.